that this first group of problems, I lost where it was. Too many worksheets, too many files. A couple of things I want to look at on this very first problem. On this first problem, it starts going through a very, very slow proof. And one of the things that I was hoping that you guys would have recognized right away, or noticed, is that they gave you 3 pieces of information. They gave you 3 bits of information, which basically means that we're going to wind up with 3 separate givens. Because a lot of times, they might write them next to each other to save space, but what I like to do is I like to give each given its own space. Because not so much right here, but in about 10 minutes when we talk about stuff that has information that we can use, like a midpoint, because that's on our progression sheet, that's the kind of stuff that we're going to write out and take more time with. So when we start problems like these, we need to look at what they gave us and kind of flow through the idea of the nuance of what their thought process is. Now, when you do proofs and you work with geometry proofs, there's so many different ways of doing it. There's so many ways of setting them up. And as long as your logic is correct, some people might be able to create the proof in 4 or 5 steps, or somebody else might take 8 steps. It just depends on how you logically put your argument together. There are certain things that have to be shown, and there are certain things that don't have to be shown. Well, we had a fantastic question yesterday. Can you reuse reasons? Absolutely. Absolutely. You might have 2 sets of substitutions. You might have 2 definitions of midpoints. You might have 3 givens. I don't know. But you can reuse stuff. There's no rhyme or reason why you can or cannot. Some proofs are faster than others. Some proofs need a little bit more definition, and that's what we're going to get at today. There's like 3 other definitions that we ran out of time with yesterday that within these 2 problems, that's probably where most people got hung up, and that's fine. I'm okay with that, okay? So, what's the reason why they wrote down HI equals 9? It's given. What's the reason they wrote down IJ equals 9? It's given. So, we get those out of the way. Now, why in the world can they say HI is equal to IJ then? Because what?
It's congruent.
They're not congruent.
No. Oh, not congruent.
Let's think back. Look at our reason sheet again real quick. On our reason sheet, we have something called the substitution property. And it's kind of a long-winded definition. If A equals B, then A can be substituted for B in any equation. Basically, this means if 2 things are equal to the same thing, I would put this on my reason bank next to substitution. That way you can have another example of the wording of it, because I'm not going to take that reason bank from you, okay? But believe me, eventually you're going to know what substitution looks like, because I have another hint for you here in a second as well. Buongiorno! How are you? I'm peachy. So if 2 things are equal to the same thing, then they are equal to each other. It's you're basically putting something in for something else. Okay? Now, a real easy way of writing that out where you could see it very clearly is the following. Another little example here. Let's say x equals 7 and w equals 7. What's the relationship then between x and w? Yeah, they're both 7, so what do you know about x and w? They're equal to each other. And my reason would be definition, substitute, or excuse me, not definition, substitution. Okay? So anytime you're replacing something with something else, when two things equal the same thing, those two things are equal because of this rule called substitution. Now there's a difference between substitution and transitive. Notice, substitution, they're vertical of one another. The same thing is vertical above one another, whereas the transitive property, A equals B, B equals C, A equals C, those two are diagonal of one another. You have transitive property written on your reason bank, correct? At the very, I think we put that on the very bottom, didn't we? If not, let's make sure that's there. This is transitive. The transitive property looks exactly like the law of syllogism. Okay. So remember, substitution is if the same, if like the value they both equal is above one another. Here, x equals 7, w equals 7. But when they're diagonal from one another, it becomes the transitive property. They're very similar, but that's that subtle nuance that gives the difference between the two properties. Does that make sense? So now when I look at that proof, when I started that, we had, was it I8, or HI was 9, IJ was 9, HI equals IJ because of substitution. Can I go back to that? You got this written down? Yes, ma'am. That's on your reason bank. I was just saying to throw this portion of it, like I was just rewording it, just kind of put it off to the side or underneath it or something. Maybe even if you want to throw it down, because you have the transitive property, I think probably on the very bottom, that little shortcut of it. If you want to put it even just next to that, because substitution and the transitive property, they look a whole heck of a lot like each other. But that subtle difference is that the transitive has got that diagonal to it. Okay. I thought we did.
Would be over here in.
Because here's the transitive property. I thought we wrote that down. Oh, we'll write that down here again in a second. All right? All right, let's go back to that little proof part here and see where we're at then. So notice, HI is 9, IJ is 9. HI has to equal IJ because they both equal 9 because of the substitution. Okay? This next step is the one step that we didn't get a chance to talk about yesterday. It is a very, very common step. I want you guys to look at how the proof started. The proof started with everything in equals, and then it switched to congruency. That happens all the time. Because if you think about segment addition, segment plus segment equals bigger segment. Angle plus angle equals bigger angle. All of this is in terms of equality. Whenever you're using math, added property equality, subtraction property equal, all those things, they're all with this equal sign. But sometimes proofs want you to show things that are congruent. It's just adding one step to your nightmare, to your problem. So when you have this stuff that switches back and forth between equal and congruent, it's a very simple thing, because if things are equal in measurement, they're congruent. And if things are congruent, they have equal measure. They're kind of synonymous, but you can't do math with a congruent sign, but you can write proof with congruency. That's the reason why we have this little subtle step. So in a square, I want you guys to write this out. Yeah.
We're gonna go back to that stuff right after we talk about it.
Yeah, we're going back
okay,
and because like I was saying, there's a couple of things that we didn't know, and that's why I'm bringing those in. That's why I talked a second ago about what substitution is going to look like and why this congruency works.
Okay.
And this is how these, and then it'll be able to fill it in real fast. Okay. So to switch, between equal to congruent or congruent to equal. You can switch between equal and congruent or from congruent back to equal with one very simple step. On your reason bank, they actually talk about it. On the very back, they talk about congruent segments and congruent angles. Line segments have the same length, angles that have the same measure. It's great. You don't need to know it that way. All we have to know is that if you're going to talk about things that are congruent, that means they have equal measure, whether it's an angle or a segment. So all I have to do then is the following. I'm just going to write this as an example. Let's say we have AB is equal to CD. Let's just say that was given to us. That means I can do this. AB is congruent to CD. Now this is the most complicated reason that we have out there. You'll have to bear with me. Don't forget to do the other side so you don't get all lopsided. It's just the definition of congruency. The definition of congruency allows you to switch back and forth. That's it. That's it. I know that some teachers say you have to say that's the definition of congruency of angles, definition of congruency of segments. I don't care. I really don't. Because if you remember that it's just because congruency allows you to switch back and forth, great. Because you know what? Once again, in the grand scheme of life, is someone going to force you to do a geometry proof to get a job?
No.
No, but you have to use logic and reasoning to make sure you have a valid argument.
Yeah.
Yes. Yes, ma'am.
So would you use the definition of congruency if you're switching from congruent to equal?
And I was just going to show that next.
Okay.
And that's why I'm saying or to go the other way. So, or, let's say it's XY is congruent to WZ, and let's say that was given, and then I wanted to switch that to equal, I would write XY equals WZ, and once again, what do you think my reason is? Definition of congruency, because that's how it allows us to switch back and forth. Whenever I want to switch between equal to congruent or to congruent to equal, my reason is always the same. It will always, always, always be definition congruency. Okay? And that's it. That's how those flip back and forth. That's how you put this valid argument together, just by saying that. Okay? So now when I go back to look at that proof that we were working on yesterday, you guys all have this okay? I don't want to go too fast. I have a tendency sometimes of going too fast. HI equals IJ blank, definition of congruent. What do you think is supposed to go there?
HI is equal.
Yep. Do you have to have those little line bars over the HI and the IJs?
No.
Technically, when you're in congruency, you're supposed to. But once again, I'm just happy that you fill in the blanks and you know the logic behind it. You know, this isn't a college axiomatic geometry course where everything that you write has to be valid. It's okay. Oh, I forgot to bring proofs for you guys. I gotta do that. Show you some stupid proofs I haven't do. I will. Anyway, so we have HI is now congruent to IJ. Why is IJ congruent to JH? Given, knuckleheads. That was that third given. It's weird. This book is sometimes from, it splits up the givens. I understand why they went from HI is 9, this is 9 to making them equal, because you can say it right away. And then they know that their next given was in congruency, so they switched it. A lot of times people wait to write some of those things out, and they just go right to writing down all the givens first. There's valid reasons for doing either one of them. And the next example, that second proof that I tried to get you guys to do, the complementary, has a prime example of something that I would not do. And we'll get to that here in a minute. So now you follow the flow here. HI is to IJ, IJ is to JH. Why is HI congruent to JH then? See, not substitution. Look at this. We have this diagonal again. What is that when you have the diagonal? What is it? Transit. Very good. Now, the idea with these proofs, guys, is that once we get going, hopefully by the end of the day tomorrow, you're going to have everything you need to know to do all the ones that I have set up for you guys for the next couple of days, between your reason bank and that progression sheet, to figure out what comes next. What's the next step, okay? And it's not going to be as scary and difficult as you may think it is right off the bat, okay? Yeah?
I feel like this is hard.
What's that?
I think this is just hard.
Well, it is. And this is the first time you have math that's not like math. It's logic and reasoning. And you guys have a hard time reasoning. And it's nothing against you. It's just a very difficult concept to wrap your head around. It's like the idea that you guys constantly skip word problems. Why? Because you don't want to read them. It's true, okay? But I'll tell you this, I know for certain, I think it was about 5 years ago, maybe 6 years ago, the very first math question on the ACT had 67 words in it. First math question has it. ACT, SAT style questions all have a lot of words from it, explaining the scenario, getting it set up. How do you reason yourself through that? That's what this stuff is going to help you perfect. The idea that you can come up with a logical way to go at a problem, a logical way to put what formulas to use, how do you set up an equation, things like that when you get to Algebra 2 next year. Because Algebra 2, I mean, geometry, we have a couple word problems thrown in here and there. A little bit more so second semester when we start dealing with trigonometry, you know, right triangles, things like that. It's much easier to come up with word problems, you know, with distances and whatnot. Algebra 2, you got word problems and what we call modeling all throughout. You're going to see a lot more of those problems that you have to reason your way through. And my Algebra 2 classes that I have right now, they're struggling with that concept as well, because it's difficult to reason what values mean. And we're just trying to get you guys to get to the idea of that you can come up with reason and logic that will allow you to do that better next year. So yeah, it sucks, it's hard, it is. But I'm not lying to you. If you trust me on this, give it a week or so, I guarantee you'll be able to do this on your own. Look at your sheet and go for it. I really do. You will. You'd be surprised. Okay? Let's look at the other one. The other one was complementary. If we look at our complementary stuff on our progression sheet, we have a how-to. Oops. We have a how-to on our complementary stuff on our worksheet, on our progression sheet. If you look at your progression sheet that talks about complementary, what does it say? What do you, if you're given complementary, what do you state? Yes, sir. Perfect. On your progression sheet, it should say angle plus angle equals 90. So in this given statement, angles 3 and 2 are complementary. There's given. Now, here's where I don't like what they did. Yesterday I told you guys, anytime you have a given statement you can work of, use it right away. We just said that that statement means that angles 3 plus angle 2 have to equal what? 90. So that means I would skip ahead to this third part, and this is using the definition of complementary. 3 and 2 has to equal 90, so there's your definition of complementary angles.
Isn't that what the second one would be too?
No, the second one, what does it say? The second one was given.
Oh, yeah.
Okay.
So just write given.
Yeah. So from time to time, they will write all their givens down first, whereas the problem before it, they split them all up. this is another one of those examples that I would have split it up. Since I know there's a definition of complementary, I'm going to use that. Well, they used it, they just used it a step away. That's all. Okay? That's the only reason they skipped ahead. So now I backtrack. I've used up everything I could from complementary because my progression told me all I can say is that angle plus angle equals 90. Well, that means angle 3 and angle 2 add up to equal 90. It's right there for us. We wrote it down. We go back in. Our other given was 1 and 2 add up to equal 90. So the second one here is also given. Now, you have two things that are equal to the same thing, which means that they're equal to each other via what? When two things equal the same thing, they equal each other. What was it?
Would it be definition of congruence?
Definition of congruence is when we're switching from equal to congruency.
I keep missing one.
Substitution. This is that substitution step again. Substitution is when two things equal the same thing, they equal each other. Okay. Since these two things both equaled 90, they have to equal each other. That's all that means. So now, when I'm looking at step 4, and then I look at what happened between step 4 and step 5, what happened? What went away? Angle 2. How did they get rid of angle 2 on both sides? Subtraction. They had angle 2 on both sides by canceling them out to get to here. All they did was a sub t prop equal. They subtracted the same thing from both sides and an equal sign. That's what that looks like. When we did algebra, we wrote out physically subtract angle 2 from here, subtract angle 2 from here, subtraction property equality. Then we would write simplify. We're starting to get away from those things because we've done that already. We can shorten up our proof a little bit by just kind of condensing some stuff if we have to. Okay? Now, last but not least, what changed between 5 and 6? They made it congruent. What property or what tells me that I can do that? Definition congruent, and I'm done. It's definition of congruent. All right. That's what that would be. When it switches from equal to congruent, just a definition of congruent. If it's congruent to equal, same thing. All right. Let's add some more into our notes here. Here's another scenario that'll happen. It's very common. But you guys write this one out here.
Is this one going to go into a box or?
No, this is just, these are notes here. I will always make a box when I want you to put something in a box. Does that make sense?
Yeah.
So let's write this one down. I want to put this in our notes. I want to add a couple more. I think I have 2. I think we got 2 more proofs to look at today. I've got, I think, 2 more, maybe 1 extra reason thing to look at, and then a couple of square things to put in together, just to try to get some logic things back down. Bless you. So, in this case here, I am given that I have segments, what is that, AL is equal to segment SK. They gave me a diagram, and then they wanted me to show that segment AS is going to equal segment LK. So right off the bat, everything written in here is in terms of equality. So do you think that we're going to have to worry about switching things around at all? Probably not. I'm not going to have to worry about switching anything around because everything's in equals. Okay. But then I also want, when we start doing this, whenever you have a proof, what's the first thing you always write down? What's given. So, this is how we start this. Sometimes when you start with just only have one thing a given, it takes a minute or two to figure out what is this even asking me? So if I write down AL equals SK. what should I do to my diagram?
Tick marks?
Exactly. Perfect. Little tick marks. I know those two smaller segments equal each other. And then I sit there and look at it and go, what is this? What am I supposed to do now? Well, if you look at what they want you to prove, they want you to prove that AS is going to equal LK. What's that? What was it? They're trying to get you to show that those the two larger segments are going to be equal to each other. Well, those two larger segments have something in common. What do they have in common? They have LS in common. See how that's overlap between both of them? See how there's that common overlap to both of those two segments? Now, when I'm sitting here thinking, all right, I have common overlap of the same thing, that means that this segment plus this segment has to equal the bigger segment. What tells me that I can add two segments together?
Segment addition?
Segment addition. On the same idea, this segment plus this segment equals the large segment again as well. So I have two different ways of writing out segment addition here. So what we have to do is something that is new. And this is actually on your reason bank right now. You just haven't really looked at it yet. So if you look at your reason bank, there's a portion in here called the reflexive property. The reflexive property basically says you are yourself. The reflexive property is you are yourself. And really, the only reason that you need to know about the reflexive property is that you use it when you have to define something. You use it to define that something is there. Well, what does that mean? That means that, really, quite literally, when you have an overlapped segment, if you're starting from here and you need to show the larger, you have to define the middle. When you have to define the middle part, when you have to define an overlapped part. It happens with segments, and it happens the exact same way with angles. It's a very common, quick step. So if you have an angle set up, if you start with this, those two are congruent, and you want to show that these two are congruent, you have to define this middle part. That's all it is. Basically, it's going to be able to show that you're going to add the same thing to two sides by defining it. And all this reflexive property does, it just tells you that it's there. Okay? It's a proper way of doing it. You can't just add things together if you don't know it's there. It's one of those weird rules of geometry. Okay? So reflexive property is for when you have to define something that's not already given to you. You will see it pretty much whenever you have to add a middle part to both sides. You will see it when you have a middle angle that you have to add to both sides. That's kind of the common way this happens. Sometimes we use it for reflexive property when we get to triangles because it's a shared side. We call it a reflexive property. It's another thing that we use a lot. That'll be in a couple of weeks still. And it's the same property, but it's a very subtle difference in how you write it. So back to here then, what's the common overlap for these two parts?
LS.
LS. So my second step then would be to define that LS is there. Because as soon as I say that it's equal to itself, I can then add it to both sides of the equation. Okay? Because if I do this, do you guys agree that 3 equals 3? Do you agree that 4 equals 4? So if I take this 4, which is equal to 4, and I add it to both sides of the 3's, do I still have a true statement? Because last time I checked, 7 equals 7. Since I added the same thing to both sides of an equal sign, what property is that? Add property equal. But in this case, instead of adding numbers, using the algebra like we did last week, I'm going to add a segment. I know that LS is the same thing on both sides. And I know that if I do this, oops, AL plus LS is going to be SK plus LS, because I'm adding the same thing to both sides of the equal sign. I keep it balanced by using that algebra property of add, prop, equal. You will utilize these addition properties, subtraction properties, multiplication properties within geometry pretty regularly. In fact, one of the questions, or one of the next proofs that I have, it does work with multiplication, but not the multiplication property of equality, but what the pure definition of multiplication is. And we'll have time to throw that one on a square here as well, I hope. So again, I added the same thing to both sides of the equal sign. What is that called? Add prop equal, good. So now look at what we have. What is AL plus LS equal according to our diagram? Why? What did we just do? You added 2 smaller segments to equal a larger segment. What's that called? Segment addition. 2 smaller segments add up to equal a larger. Once again, what's SK and LS? It's LK. Didn't I just use segment addition twice? 2 smaller segments make up the whole. Make up the whole to make up the whole. You're done. You defined it, you added it to both sides, 2 smaller segment makes the large. Done. Works all the time for that type. So when you see, if you do ever get one that you have an angle set up like that, if you have these 2 that are equal to each other, define the middle, add it to both sides, and then you're the same. Because when you add 2 angles together, what are you using? What is it? Angle addition. If I'm adding 2 small angles to get a larger, it's angle addition. If I'm adding 2 segments to get a larger, I'm using segment addition. You would be surprised how many people mix those up. Because angles look like segments, and segments look like angles. Yay. Okay. Is it becoming a little less fuzzy with every passing one we do, I hope? Can you start to see the idea that we have the information, it's a matter of basically putting 2 and 2 together. How do I get that next step? By using some of these little properties that we've used before. Let's try this one. Here. Midpoints. This was the very first progression that we wrote down. Go ahead and write that down, and let's get our diagram drawn up, and we'll go from there. according to your progression, what's the first thing you would write down after you're given a midpoint? Segment equals segment. Good. So we start with our given. M is midpoint of AB. Given. So if M's the midpoint of AB, my progression sheet tells me state some segment equals to some other segment. Well, in order to be able to figure out which two segments they are, you go to your diagram and go, hallelujah. They're right there. And then you know which ones to write down. Progression sheet told you you were given, the problem told you were given a midpoint. Progression sheet told you what to do. Write down segment equals segment, knucklehead. That's what it says. AM equals MB. What's your reason? Very good. Definition of midpoint. Make sure you guys are writing down definition of midpoint. Don't write down midpoint because that'd be wrong. Okay. Have I utilized everything that I can from that progression part? Last time I believe on our sheet only says one thing, segment equals segment. This problem has something to be proved in terms of equality, so do I need to worry about writing those two segments as congruent to each other? I don't need to worry about that. So I go to my second given. My second given says B is the midpoint of MD. So it tells me that B is the midpoint of MD, which means I have to also write out some segment equals some other segment, but what two segments are equal? Well, according to my diagram, MB already has a single tick mark, which means BD should have how many then? A single, because they have to match up. So that means when I write that out, I now have two segments to say that segment equals segment for my fourth step. MB is BD because, very good, because of the definition of midpoint. Right. So at this point, you've used up all of your givens, which means we have to now start to look at what we have to prove. Well, they want us to prove that MD is equal to twice the value of MB. Well, MD is here. Okay? According to our diagram, what is MD made up of? What was it? MD, sorry, the letters sometimes are tough to hear. According to our diagram, MD is made up of MB plus BD. Why can I say one segment is made up of two smaller segments? Segment addition again, very good. Well, it's very close to saying what we need to get to. But I want you guys to realize something else. What does that equal? 10. Thank you for not taking your calculators out. Isn't this the same?
Yes.
5 groups of 2? Multiplication, remember, is repeated addition. So multiplication is your repeated addition step. So if I know that I'm going to multiply, if I have those 5 2s, or we're going to get it out. If I have 5 2s, that means it's 2 plus 2 plus 2 plus 2 plus 2. if I want to have two segments of MB, that's the same as saying MB plus MB. Do you agree? Now, using that logic thought, MB equals BD, which means when two things equal each other, you can replace it somewhere else. Substitution. And then lastly, and the reason here for this one, I wouldn't say solve, since we've gone from repeated addition to multiplication, that is just the definition of multiplication. So definition of multiplication is, if you want to remember it as, you don't see it all that often, but if you want it, you can only use that whenever you have repeated addition, and that's how you switch it to that. I have 3 fill-in-the-blanks for you guys to work on tonight. Let me pass these out here, and I'll write down which ones they are before we run out of time. You might not, don't forget, when you get down here, did we add stuff to our regression sheets and our other stuff? You might want to take a picture of it, make sure you didn't lose anything. You don't lose anything, you lose that. On these, there's more than 3 pages, but on page 1, the algebra, on the bottom of the page, and I forgot, I apologize, guys. I totally forgot to write down problem numbers when I was cutting and pasting all this together, so you just kind of have to bear with me here. On page 2 is the segment proof. On the bottom of the page. And on the 3rd page, it's the angle proof. On the bottom of the page. Okay? So there are 3 problems I'm going to ask you guys to do. Yes, ma'am. Oh, you didn't. Oh, I didn't count. I can't count to 10. I'm very. Maybe I don't have enough fingers. So the bottom page, first page, bottom one is the algebra proof. Second page, the bottom one is the segment proof. Third page, the bottom one is an angle proof. I just want you guys to try and get through those 3. You will find out that they mirror pretty much everything we just did. Have your notes, have your progression sheet and your reason bank, and you'll be able to follow through those. We'll take them a step further tomorrow. The 3 bottom, the bottom page is the first. The 3 problems in the bottom of the first 3 pages. It makes any sense. To me, it made sense. Okay? I wrote it on the board and explained it 4 times. So which ones do you think you should do? Which ones? Uh-huh. Uh-huh. Yes. You were looking at me like I was like really crazy about that. Yeah. Yep, those are the only just the page 1 bottom problem, page 2 bottom problem, page 3 bottom problem. Try to make it that simple so we don't have to figure it out. I just completely forgot to number them. So thank you. Yeah, it does it from time to time. Thanks guys, have a good one.